Hi.
Hey, Sione, how's it going?
Good. How are you?
Oh, doing pretty good today.
Good.
All right. How far along did you get in the um studying so far?
Good. I'm sort of reviewing everything that we've done in the past. Um, trying to do the review questions. Let me share my
Okay,
screen.
can you see it okay?
Yes.
If you want to show that there's no greatest integer, what would be a good way to purchase by contradiction?
Um,
Suppose that there is. So we're saying that there's no greatest integer out there. That's the biggest one. So let's say there is one.
yeah.
So in order to capture this idea of greatest common or the greatest integer, first off, we'll say let x be an integer such that for anything else out there that you can find, oops, we
Oops,
turn
sorry.
pages again. For any other integer out there, we know that x is always going to be bigger than y. Because if x is not bigger than y, it's not the greatest one.
Yeah.
Okay? Now, because x and y are both inside z, what can we say then about x plus y? It's back inside z due to closure. So if you have x plus y, I know that's going to be bigger than x as long as y is bigger than 0. But I can pick anything I want up here anyways. I'll just pick it so that it is bigger than 0. And then what that says is I found something that's bigger than x. So there's no way that x is the greatest integer. So I can always go a little bit further. So the assumption must be wrong. The assumption is here, it's not that I can't pick an integer. The assumption is for any other integer out there, I can't have that. So there cannot be the greatest integer within the set of z. Remind me again, what's the structure behind contradiction? What am I really
Um,
trying to prove or disprove?
the opposite. So if you disprove the opposite, then what this original statement is true.
So I have this statement for the conditional statement, and this might be really hard to do. So we go about the opposite by doing the contradiction, and the structure is P and not Q. That's the structure you follow all the time when you do contradiction.
Mhm.
Okay, so we'll go ahead and let M and N be integers such that M times N is odd. And by definition, there's going to exist some integer k such that mn equals 2k plus 1. So the not q part is here we have n and m are both odd. What's in the negation of that phrase?
Um, N and M are both even.
Say it one more time.
N and M are both even.
Oh, so close. N or m
Yes. Yes.
are both even. We'll say even. So either this one or this one. And as soon as you bring or into the conversation, you are talking about cases you do have to consider. So you got to consider case one. Suppose that n is even. And let's say case two, m's even. Now, they can both be even. I mean, you could have the case three where you have this one and you have this one. But as long as I don't talk about m at all being even or odd in case one, case three is actually going to follow case one. And likewise, it's also going to follow case two. So I'll just make m arbitrary and not worry about anything else. Case one. If I have this, then by definition, there's going to exist some kind of integer such that n equals 2 times L, since it's going to be even. Okay, now, the next thing is I do want to link this up. 2k plus 1, m, n, and now I can replace n with 12, just like that. Move some things to the side. And let's factor it out at the exact same time, just to save a little bit of a step. I'll take this and recalibrate it. Call it eta. Looks like a cursive script in, Greek letter. And because it is an integer, we got to make sure we have that piece. Then we can invoke the definition. Of divisibility, 2 divides 1. Contradiction. And one way if I write contradictions have two arrows smashing together, like you have two cars about to collide. Contradiction. The contradiction, the part that we contradicted was this piece right here, where we say, okay, that's not Q. Now, technically, when you're going about this, you do need to run through case two, because case two might be different from case one. We don't really know. But there is an aspect of symmetry in this problem. And sometimes what we do to make it a little bit easier, we can say 2 divides n. We can say this is similar. Case one, just make sure that is similar. And then you can bypass a lot of complexities. So you don't have to worry about writing it all out again. Okay, so regardless where you go, case one or case two, we run into a contradiction. So what that would then indicate is when I come back here, like the problem statement, if this is odd, these things better both be odd. Otherwise, you got a problem. Okay, any questions on that?
So we don't have to do the third case, right? Like the N and M.
No, because that's actually embedded within case one and case two, actually.
Okay.
In case one, I just said, suppose that n is even. Did I make any statement on m?
Mm-mm.
No. So m could be even, or it could also be odd. It captures both of those essence because I didn't say anything about it. So if I was to write out a third case and say 2 divides n and 2 divides m, I can really turn a blind eye to this and just do exactly what I did over here. I mean, exactly what I did over here. And I get the exact same proof. I didn't have to know m. If I did know m, I can put it here and say 2 whatever the m is and plug it in, but it's not going to help out at all. Okay, so let me cross this out, the if and only if, and let's just say we're going in this direction. See if you can put together some kind of proof real quick for number 4.
So without the if and only if, what would the statement read? Like it'd be an integer n is odd when n plus 1 is even.
So it's just saying something along the lines of if 2 is odd, then n plus 1 is even. So here's P
Mhm.
and here's Q.
I thought we wrote that an integer was odd if we did like n plus 1.
2n plus 1.
Okay. So if I were to prove this by contradiction, then I'd say like let 2 plus n, or if 2 plus n is odd, then n plus 1 is odd as well, because we're negating the Q statement.
Mhm.
Oh, okay.
Good. Okay, now see if you can take this further and see if you can find a contradiction.
Would I have to do like cases for this problem? Or
You only do cases if you have an or statement. Do you have an or statement in your proof?
no, it's just and.
Okay.
Um, because I honestly can think of a number I think that would fit the statement.
Okay, tell me that number.
3,
Okay, so 3 is odd, but 3 plus 1
4,
is
and
4 odd?
no.
No, it's not.
But wouldn't that like show that it's like a contradiction then? Or am I wrong? If I
Um, that wouldn't fit it because that's get you a false statement here. What we're saying is we can find this magical integer so that when you look at it, it's odd to begin with. And it's also odd when you look at n plus 1. So 3 is not going to work
mm,
because 3 is odd, but that's 4 is even. And it's not the integer you need for both be odd. So you got to figure out another integer that's going to satisfy this if you want to prove it. Now, this is a little challenging, isn't it? N divides this division. So why not make a beeline as fast as we possibly can to an equation that we can manipulate?
yeah.
Okay, there we go. Okay, so if I have this equation right here, we use that part, but I didn't use this part yet. What do you think I can do to get this part into the problem? This is what I would do right here. Add 1 to both sides. Because I know what n plus 1 is. That's 2l plus 1.
Mm. Then factor out the 2.
Factor out the 2. Bring the l over. And notice how we keep getting run to that same thing over and over again. Does 2 divide 1? No. Now, you have to articulate that you're looking at k plus 1 minus l. And let's just call it j now to use j yet. This is going to be an integer, and we can stipulate this is due to closure. So by definition, 2 divides 1, which is the contradiction.
Would this be like 2L or no?
No, because we're going to factor out the 2. We're going to kick it to the other side to be minus 2L, but when I factor it out,
Oh, okay.
just left with L.
Okay.
This one right here, it says parity. That just means even, odd. So if this is odd, then M and N have opposite parity. And it's just a nice compact way of saying case 1, N is even. M is odd. Case 2, N is odd. M is even. Why don't you take this case right here and see if you can develop some kind of contradictory argument to prove the claim. And as soon as you got your argument, put it up here and let's take a look at it. Okay, so what's your phrase you're going to start your proof off as?
It would be let.
Mm-hmm.
Okay, so let n plus m
Okay, so M plus M.
be odd.
Good.
Um,
And
um, and well, we'll do case 1. So like n is even and m is odd.
so they have to have the same parity, the opposite of that.
Mm,
So if we're going to negate this, we can say same parity N. We'll just say N is even and M is even. Okay, what's the next thing you would do?
Assign equations to each.
Good, good. So what's your equations?
So for um, if they're both even, n would be, or each would be 2 goes into n,
Mhm.
2 goes into m.
So you can see if I'm going to lines up by definition of being even, being divisibility is going to exist integers k and l such that you have that set up.
Okay.
Now, there's one more thing up here we didn't really do.
Assign a variable to n plus n.
Mhm.
Okay.
So maybe let's call it j. Now it's time to put it all together. that came into again?
Oh, I see.
Do you see how this keeps popping up quite a bit?
Hmm.
Okay. And then you do the same thing. You say that that's the integer that's important because you can't use the definition divisibility without saying that's the integer. Because I could, again, I can say things like 2 times pi and equals x. It doesn't mean that x is an integer because I have 2 times something. So I do have to make sure that that 2 times something is that something is an integer. And as soon as you establish that claim, then you can use the definition of divisibility, and then it's going to apply 2 divides 1, contradiction, QED. Good. How you feeling about it?
Okay, I feel better. I'm starting to see that there's a structure, so that
Mhm.
helps me. Um, just because sometimes when I look at these problems and I'm like, I don't even know where to start because it's like so like I don't know, it's a little intimidating. But that's how I felt about everything else we've gone over, to be honest. But then once I figure out that there is a structure, it like makes me feel less intimidated.
Glad to hear that.
Yeah.
Okay, so try number 6 by yourself and route your problem statement as soon as you figure out what it is going to be. And let's not worry about the if and only if. Let's just say if, or let's
Okay.
just do forward direction.
So the only part of the statement that we're like um changing, I guess, like saying the opposite of is the Q, which is N is odd, right? Not the first part.
That's right. So you keep P intact and you're going to say not Q.
Okay. Um,
So you don't want to say this part quite yet. You could, but it might be better to back up and say and because you are directing your attention on n to begin with.
okay.
N is even. Now, once you establish this part of the problem, then go ahead and invoke the definition of divisibility.
The definition.
Of divisibility. In this case, this particular type of divisibility is even.
Mhm.
Okay, so I'll just take it from there now.
Um,
Okay, so you got that part. Do this
now,
part right there as well.
okay. Um, would I also do a definition for that as well?
Mhm.
Okay.
Now, there's a few ways of how you can approach it. You could simply do like a copy and just replace the K with J. That's okay. You can also come over here and just put a J right inside there because you're saying there's going to exist some K and some J, and there's no connection between K and J if you write it like this. Uh, if you were to write it that says there exists a J and there exists a K, then you can see that K is almost based upon what's happening here with J,
Mm.
and you can get a little confused if you approach it from, or at least you see it from that viewpoint. So oftentimes people will just come in here and put it inside, so you're not going to confuse the nested quantifiers. So let's just do it like this right here, and we know that. And I'll put it back over here. N squared 2n plus 3 equals 2 times j. Okay, now you got your equations. What can you do next?
Um, so click now. Um, let's see. Would I substitute every N with 2K?
I think that's a great idea. But let's start off with the equation. Give us some kind of anchor point. Now we'll go ahead and plug in. Okay. And give you a little more room there. There you go.
So would I boil it out then? Okay.
Just a little bit.
So hmm, would I move the 4k squared plus 4k to the left side and then factor out a 2?
I would put all the even together. So like what you have right here, I'd probably move all those over to the other side like that.
So I wouldn't factor out a 2 then?
Oh, yeah, yeah. The next thing is factor out too.
Oh, and then we have 3 over 2, which is
Well, you can't say 3/2, but what I know is I know that if J, K, and 2, they're all integers,
Mhm.
what can I say about that?
Oh, it's there. That side is divisible by 2 then, right?
Right. So it's going to say 2 divides 3. By definition of divisibility.
Hmm.
Does 2 divide 3?
No.
No. Contradiction. And that's how you find a contradiction in this proof.
Oh,
Now, whenever you write this up for a grade in your class, just make sure you articulate it all the way. Make sure you tie everything together in the very end.
okay. Okay. I think I'm starting to get these.
See if you can develop a proof to show that there's no integer solutions for this problem.
What is the this term mean, just out of curiosity?
Diphene, diphene, it is an equation in which it only has integer solutions.
Oh,
And probably the one you're most accustomed to is a squared plus b squared equals c squared, Pythagorean theorem. As long as a and b are integers, then c is also going to be an integer. Whenever you're looking at what's called Pythagorean triples. Now, diphene, that's a term that goes back to antiquity, Greek time, just like Pythagorean. So that's where that term comes from. But I can really cross it out. And it wouldn't take anything away from the problem because we're still trying to show there's no integer solutions to this equation.
so if I'm doing it by contradiction, I'd show that there are solutions, or
You could, but there is a really clever way of doing this. What do we do on the last few problems?
um,
Kind of the aha moment.
yeah,
Gotcha. We kept coming down to here where we had our equation, and what do we do next?
substitute and like move around the equation.
And we factored out the common term.
Yeah,
What's common between 21 and 30?
3.
Factor 3 out. And if a and b are both integers, the addition of this is also an integer. Does 3 divide 1?
Mhm.
No. So if you see that on your exam, that's how you work the problem in less than a minute, and you get what 10 or 15 points for the problem's worth.
Wow.
It really is that easy.
Okay.
And I really want to look at this problem. Show that the square root of 2, it's not a rational number. So if it's not an irrational number, another way of phrasing this is the square root of 2 is irrational. Okay, so I got to bring in certain definitions into the mix again. Otherwise, I'm sunk.
Mhm.
What in the world is a rational number? That's the first thing I got to address. Well, a rational number, loosely speaking, it's a number that you can write in terms of a fraction. But it's not just any old fraction, because an irrational number, something like pi, pi is irrational. Square root of 2 is also irrational, but we'll show here in a moment. But you can definitely take pi and write it in terms of a fraction. I can say pi over 1. So it's just not writing in terms of a fraction. What it is p and q are both integers, and q is not 0. Because I don't want to divide by 0. Okay, so that's usually the working definition you're going to be using as you're going through these problems. So things like if I have 4 over 1, or 8 over 2, or 12 over 3, those are going to be rational numbers.
Mhm.
Now, 8 over 2 and 12 over 3, they're all going to correspond to the value of 4 in the very end. So when I'm working through this, what I would like to do is have a nice simple form, a reduced form. Because I don't want to keep going through here and saying P over Q, has it been already been reduced? I just want to make the assumption, okay, it's been reduced. If I have A over 2, I'm just going to reduce it down to 4, and I'm not going to worry about it. All right. Now, with that said, if I want to show that the square root of 2 is irrational, that's going to be really complicated to do directly. So we circumvent the complexity and take it from the indirect perspective. And we're going to say, I think you're lying to me. Suppose not. You say it's irrational. I say it's rational. Let's see who wins out. So we're going to assume for the moment that the square root of 2 is a rational number. Then, by definition of being a rational number, I note that there's going to exist integers, p and q, such that I can take the square root of 2 and write it in terms of p over q. And again, I don't want to worry about, has this thing been reduced? Let's kind of reduce it all the way down. And the way I can state that is I can use this nice little phrase called without loss of generality, W log. So I'm not taking anything away from the problem if I just assume that the greatest common divisor between P and Q is 1. So there's no common factors. If I had 12 and 3, the greatest common divisor between those values is going to be 3, because 3 is going to divide into both the values. If I had 6 and if I had 50, well, 6 is going to be 3 and 2, and 50 is going to be 25 and 2. So the greatest common divisor between these two is going to be 2. So what I want is I want it to be 1. And there is a certain phrase in mathematics that talks about whenever the common greatest common divisor is 1. This is sometimes referred to as being relatively prime. So we see that phrase. That's what this means. There's no common factors between them. Just like with a prime number, the only prime factors are going to be 1 in itself.
Yeah.
Okay, so that's the step behind the problem. Now, we got an equation, like with the other problems. Let's just kind of run with it, roll it and see what happens. And I don't really like working with fractions that much. So let's get rid of it. And one way to get rid of it is multiply both sides by q. So we'll have root 2 times q equals p. And I don't really like radicals in life or in mathematics. So let's go ahead and get rid of the radical. And radicals are definitely afraid of squares. So let's throw a square at it and square both sides. Now I have that. But what do I have on the left? 2 times n k squared or q squared. That's an integer since q is an integer. What I have on the left is an even integer. And remember the other day when we proved the statement, if 2 divides n, that means 2 divides n squared. And we show the reversal, the sufficiency. If 2 divides n squared, then 2 divides n. Let's just call that lemma here for this problem. By the lemma that we showed the other day, we know automatically, first off, by definition of divisibility, 2 divides p squared. Therefore, 2 divides p. Let me stop there because that's pivotal in this problem. See if it makes sense.
Yeah, I think if that makes sense. Yeah.
Good. Okay, so what does it mean then for a number to be divisible by 2?
It's even.
So by definition of being even, I know without a doubt there's going to exist some integer k such that I can take p and write it as 2 times k. Okay, well, let's do that. Let's take that and drop it in. Therefore, we have root 2 q p, but p and o is 2 times k. So I'm just going to take it and I'm going to replace it. Well, I got that radical again, and I don't like radicals, so let's go and square both sides. If I square the left, I'm going to have 2k squared. What happens when I square the right?
4k squared.
And let's divide both sides by 2. Well, what does this say then?
The right side is even. 2 goes into k squared.
And by the lemma that we showed the other day, 2 divides q. Now, we have just arrived at the contradiction. Where's my contradiction?
Mm. Oh, we said they were P and Q are relatively prime.
What can you say about that?
So the GCD, that means that only one goes into it. Well,
And what do we find?
we found that they're both even.
They're
That
both even.
Q, so that means
Exactly. That's it right there. So we made the assumption that they're relatively prime. We divided out the common divisor, and there's nothing else there. Oops, I guess we didn't do what we were supposed to do, and we found two again. So if I keep doing this over and over and over and over, I'm always going to get this two that keeps spiraling. I'm going to go down this infinite descent of absurdity,
Mhm.
contradiction. And that's it. But we assumed that the greatest common divisor between P and Q is one. And we just found that two is going to divide the greatest common divisor. It's like that problem we keep coming up with. Does two divide one? No,
Mhm.
contradiction. What do we actually contradict then? Go back to the very beginning. Where was our initial assumption?
Our assumption was that the square root of 2 is rational,
So what can I conclude then?
and it's irrational.
And there it is.
Why did we say that we just found that 2 goes into the GCD? Why isn't it just like 2 goes into P and Q?
Well, it,
Like, how
it
do they
does. It
work?
does. Uh, there could be possibly something else up there to this contradictory argument. We know that two divides P and divides Q. I don't really know if, I'm getting some absurd statements now and getting like a vacuous kind of idea. Maybe six goes into as well, or maybe 11 or 13. I just don't know. But what I do know is two is a common factor between P and Q. And this talks about all the common factors. So maybe it's two and three, and also maybe seven. I know two is going to divide the number because two's in the mix. So you could phrase it like this. It's just a little bit more accurate. Or you could just say that P is even, Q is even, common divisor is two, not the only common divisor, but two is a common divisor. Can't happen.
Okay.
Good. That's awesome that you saw
So
that.
this would be something like very similar to the question on the review when we say that, or we're trying to prove that
Absolutely.
root of 3 is irrational.
And that's leading me to my next question. How would you take this proof and adjust it so it fits the one you're looking at?
So I'd say assume that the square root of 3 is rational. Then by definition, there exists a P and Q that are integers such that the square root of 3 can be written as P over Q.
Mhm.
Um, I'd still write the W log, right? That means that the GCD of P and Q would be 1.
In W log, what that means again is without loss of generality, you're not taking anything away from the problem by dividing out the common terms, and you're not adding anything to the problem by dividing out the common terms.
Okay.
Yeah, it's basically
Um,
the exact same thing.
okay.
The only caveat you got to worry about is this piece right here. Two divides n, if and only if two divides n squared. And you can actually take that lemma and you can generalize it. So let's say if p is prime, if p divides n, then p um, is going to divide n squared. That's how you'd make that more generalized. Two is prime. What's three?
Uh, odd prime.
It's the first odd prime number. You could do the exact same thing with root 5, root 7, root 11. So any square root of a prime number is irrational. And the proof is basically right here. Johnny, any questions on that?
So could I try to do this and then check in with you if I did it right or not?
Oh, absolutely.
Perfect.
Now, I did want to show you a few more problems here before we close up. Okay, so we basically already did 11, just slightly alter the proof we did there for root 2. But I want to jump down here to 13 because you might see that on your exam. Whenever you're trying to show something's irrational, in general, what you're going to do pretty much, I would say 95% of the time, particularly in this class you're in, take the number and assume that it is rational. Okay, so make sure you do stipulate what P and Q are and do stipulate that Q is not 0. Then from here, it's a mad rush to try to simplify this thing down. And I know something about root 2. So let's kick everything else over to the other side. Subtract 1 from both sides. Common denominator is Q. Divide both sides by 2. And if P and Q are integers, then so is the numerator and so is the denominator. But what is this saying? I already know the square root of 2 is irrational. And what I know about the right-hand side, it's rational. Can an irrational be rational? No. That's how you work these problems. That's the contradiction right there.
What if on the exam this was the only problem and like does that mean that in the proof that I have to prove that square root of 2 is irrational?
I would not require a student to do that for problem 13, but do ask your professor to make sure if that's something that you need to do. That's usually something you don't have to typically in these problems right here with 13, also 14. You bring that into the mix.
Okay. Maybe I'll send her an email and ask.
Yeah, I would definitely do that. More than likely, she's going to say, no, don't worry about it. Now, just to show you 15 and 16, if you have log base 3, I see it's irrational. So make the assumption you're lying to me. It is rational. And I don't really like logarithms. So I can incorporate properties of logarithms and exponents. And the property you want to incorporate here is you can power this thing up. Argument pops out. Now you have this. And power both sides up to the qth power. So you're going to be using this property. So take the right side, power it up to the qth power, power this up to the qth power. What do I have on the left? Powers of 2. What do I have on the right?
Powers of 3.
And on the left-hand side, if I was just to sneak out 1, 2,
Q
and,
minus 1.
and of course, I'm making the assumption that Q is going to be at least 1 for this to happen.
Mm-hmm.
But if I take an integer and I power it up, get an integer. Does 2 divide 3 or any multiple of 3?
Mm-hmm.
That's how you find your contradiction in those proofs. So you got to know a little bit about logarithms and exponential properties to get down the air. But in all these problems, notice that there is this pattern. Say equal to a fraction, find the contradiction, and look at the properties of division and being even and being odd.
Okay.
Good. Well, Sonia, how you feeling about things here for the day?
Good. I feel better about these. Um, I think I'm gonna just try to do them again and then maybe look at or definitely try to do the ones that we did again and see look at the usually what I do, I'll look at the notes and see if I can do it by myself.
Mm-hmm.
And then a lot of the times like I will like change the proofs for different numbers. So that's probably what I'll do for the irrational, like the square root of three. And then I'll check in about that tomorrow and see if I did it correctly.
Sounds good. Sounds good. All right. Well, we're making some good progress here. Like you said, just go back and look at the problems again. Make sure you understand the concepts. And anything you don't understand, let's talk about that tomorrow. Make sure you do understand it.
Okay. All right.
All right. Well, keep up the good work, and I'll see you tomorrow. All
All right. Thank you so much.
right. Take care.
You too.